So, have you heard about the fourth dimension? Maybe in Einstein's laws as time, but what if the fourth dimension is not time, but of space that works just like the first three dimensions we're familiar with? Can we see 4D objects then? You may think it's impossible. We are confined into a three-dimensional world, but maybe there's a way. The space we live in consists of three dimensions. Physically, there's no more, just that. But if we see it in a mathematical perspective, number 3 is not relevant. It is possible to have dimensions lower than 3. 1D is just a straight line, and 2D consists of a plane. Geometry doesn't block us from having only 3. We can deal with more than 3 spatial dimensions that lie perpendicular to our cardinal directions. This space that is described with 4 dimensions is called 4-dimensional space, and we will label it with a W. So, is it possible to visualize 4D? Let's explain something first. You are seeing everything in 2D. Your phone, your computer, and even yourself. Yep, our retina has a 2D surface area which can detect light coming into our eye. What we see is not 3D, but a 2D projection of a 3D world we're looking at. Our brains do all the other work. We infer 3D depth. The same happens with 2D beings. Imagine we were one. We would see something just like this, only one dimension. But thanks to our brain, we can infer 2D depth. Using this analogy, we can infer that 4D beings must have a 3D retina, which assumes 4D depth. Isn't it just amazing? Let's start with the bare minimum, with a 1D world. Inside this, everything's like a piece of string. We can only extend or retract it. And as you can see, every string is delimited with a point, which is 0D. Let's move one level up. As you may know from your math classes, a 2D world is a plane. Here you can control the width and height of an object. And similarly, as the 1D world, every polygon has a boundary, in this case, line segments. Time to reach our world. 3D objects are far more interesting. We can manipulate width, height, and depth. And as you may think, 3D objects are bounded by 2D planes. Can you see the pattern here? An n-dimensional object is bounded by n-1 dimensional objects. So, if we apply this to a 4D object, well, it must be bounded by 3D things. Let's name this guy Tommy. Tommy realized that some objects are behaving a little bit weird. They're scaling up and down and changing colors like if it were magic. Tommy is really confused and needs your help. But you're confused too. But there's a difference. You are a 3D being while Tommy is not. Oh, does it make more sense now? That wasn't a square that was behaving weird. It was a cube, and it was changing because Tommy was moving in the third dimension. This is a way to understand how 4D objects behave. For example, this is a cross-section of a 4D hypercube. And if we play around with it, we can clearly see that it is disappearing. But what is really happening is that the hypercube moves in the W axis. As you can see, this is a fun way, yet not the best, to visualize 4D objects into our 3D world. I said this was not the best way, right? Why did I say that? Basically, you can't get a clearly image of the object. Based on what you've seen, can you get a clearly image of a hypercube? Probably not. And you may say, it's because we're not used to 4D objects. Okay, so I'm gonna put some cross-sections that 3D objects make inside a 2D world. Can you guess which object it is? Even if you are surrounded with 3D objects, you can't just know which figure will make a specific sequence of cross sections. Can you see what's the main flaw when we're trying to visualize higher dimensions with this method? To solve that problem, we're gonna use projections. Projections are a more straightforward method to explore higher dimensions, because we're not dealing with bits of information. Instead, we're having an integrated view of the object. This is a 3D cube projected using orthographic projection. It looks as though a square, and that's due to we're looking at it face on. Now, this is the same cube, but using another projection type, called oblique cube. As you may see, we can clearly identify all 6 faces quickly. Now, this is a 4D cube projected using orthographic projection. Interesting, right? Now, this is the oblique cube projection of a 4D hypercube. Instead of faces, we see cells. Let's interpret this. Remember, 4D objects are bounded by 3D objects. Thus, this hypercube must be made out of 8 cells or cubes. It doesn't make much sense, right? Because you're not used to. Let's go back with analogies. Here we have a 3D cube projected into a 2D plane. If you interpret as a 2D being who doesn't know anything about 3D objects, you see a square with 4 trapezoids. Now, what if we rotate it? You can clearly see how those 4 trapezoids are changing their sizes, and how the middle square disappeared. Remember, you don't know anything about the 3D world, and you can only interpret 2D figures. So, when we try to see a 4D projection, it's basically the same. We only see a 3D cube doing weird movements. I would love to keep talking about different methods to create good projections or how to infer 4D depth, but we ran out of time. If you want to learn more though, I encourage you to visit this page. It's entirely dedicated to 4D visualization and figures. That's all for me, I hope you enjoyed.